And welcome. Today we're going to be talking about giving an example of a mixture problem involving a time varying concentration. Now I've shown you this problem before in class, but what I want to do is just go over things and redo the solution with a little bit more context. Okay, so let's start with our standard mixture scenario. We have a faucet putting water in to a large container as follows, and then of course we have a spigot on the other end of it there, and so we have the volume of this container is going to be we'll say it's 5 liters, and we have a rate in, which I'm just going to say is 1 liter per hour. Okay, and a rate out will also be 1 liter per hour. Okay, in addition then we're also going to have now we're going to have a C in, our concentration coming in, so this is R in. We're going to have some sort of concentration in. This is going to be a salt concentration, a salt mixture, a salt solution, and that's going to be of the form T times e to the negative T. Okay? And what this does, the kind of graph this gives in terms of concentration, then it looks a little like this. Okay, all right, so the question is then, if this is the salt concentration that we're going to send into this tank starting at time equals 0, what's going to happen then to the salt concentration in here? What is the x of t? So then we define x of t to be the grams of salt in the volume. Okay, so that means, of course, then that C out, and that's going to be a function of time, will just simply be x of t over v, because that, of course, is grams per liter. Okay. All right, so there's our basic situation, and we have that R out there. All right, so let's write down what this differential equation is. So as before, we can write down the time derivative, dx dt, the rate of change of the amount of salt in the tank will equal R in times C in, which now is a function of time, which we're using as that. And then it'll be less R out times C out. We can rewrite this now as R in, of course, is 1. C in, of course, is T times e to the negative T. And then R out, of course, is also 1. And then C out is going to be equal to x of t over v. Okay, and v, of course, was 5. All right, so I'll erase here and put in that 5. I can clean this up a little bit and have I have a dx dt is equal to negative 1/5 times x plus t e to the negative t. All right, so we can think of this as our constant. A lot of times with these differential equations, actually, let me back up here a second just to get my notation right. What we want to do is actually find the linear part of the differential equation. The linear operator involving only x will be plus 1/5 x is equal to t e to the negative t. All right, this parameter there, we can think of that as what we call our k is then going to be equal to 1/5. All right, so, and then finally what I'm going to do is I'm going to say my initial condition, x of 0. I'm going to say at the beginning our tank is actually going to have no salt in it. So I want to know what happens if I start at time 0 and I give it a squirt of a salt concentration that I'm going to turn on at time 0, but eventually that salt concentration will be on the wane. The question then, what does the amount of salt in the tank look like over time if I give this little pulse of salt? So you can think of this as sort of like a temporary pulse of salt solution. And I want to know, basically, the question, I guess, we're going to answer in the most kind of abstract, or I guess just, I shouldn't say abstract, but just qualitative terms is, what does C out look like? Given the temporary pulse in. Okay, and that's the qualitative question we want to ask. So we expect that it's going to take a while, that we're going to get something that's going to go like this. The salt concentration will go up, but it might be somewhat delayed before, and then it'll eventually decay back down as well. So that would be my guess. And we'll put a question mark on that. But let's see if we can get some insight by solving the equation. All right, so let's do this. Okay, so let's, again, our differential equation was dx dt plus, and now I said that it was a k, and we know that k is equal to 1/5 in our particular parameters, but let's just do this for more general parameters. And we know that our x at time 0 is equal to 0, but I'm going to say that I'm just going to call that x naught. All right, and this way we can see what the solution looks like for more general parameters. And then later on, of course, if you want, you can mess around with choosing new parameters for your model and see how solutions change by changing maybe the size of the tank or the amount of the rate at which we put water in and out of the tank. Okay, so that's kx equals t e to the negative t. Okay. All right, so we can solve this equation using a first-order linear method. So what we're going to do is, of course, so we got to find integrating factor. Okay, so of course we see P of t is just equal to k, and Q of t is equal to t e to the negative t. All right, and rho of t is always going to be equal to integral, or e to the integral k dt, which is equal to e to the k t. All right, so now we multiply the integrating factor by everything. So we take our differential equation, and now we're going to multiply the integrating factor by everything. And what I've done there is, of course, e to the kt times e to the negative t is equal to e to the k minus 1 quantity times t. All right, and that's just some algebra. Now this, of course, looks like the result of a product rule, so we can then, of course, wrap it back up inside a derivative there. And now we have this, e to the k minus 1 quantity times t. All right. And then, of course, what we'll do then is then integrate. So the key to integrating this is to realize that this is also a function of time for x. All right. And again, that's our unknown solution that we want. All right, so what we're going to do is integrate, and I'm going to integrate starting from 0, because that's the starting time of which my initial condition is going from, all the way to t sometime in the future. All right, and then I write x of s, e to the k s ds, and these s's here are dummy variables. Okay. And that's equal to, now on the other side, integral, so that was this side of the equation. Oh, sorry, I have to put that prime there. I forgot that. Sorry about that, guys. And that prime, of course, comes from here on the outside. And then finally, e to the t of s e to the k minus 1 times s ds. All right. And that again is also a dummy variable there. All right, now let's go to a new page and finish this calculation up. What we had was 0 to t of x of s e to the k s ds equals integral 0 to t of s e to the k minus 1 s ds. Okay, sorry, there's a prime there as well. All right, so we know the antiderivative of this is going to be x. Sorry, that has to be an s in there. Sorry. X to the s, e to the k s. We're going to evaluate that at our limits of integration, which is 0 to t. And that's equal to on this side. And now I'm going to start this integration. And what I want to do then is, of course, use the integration by parts technique. So I see that this has a nice antiderivative. So I can write e to the k minus 1 s all over k minus 1, because that's the antiderivative of this piece right there. And then we multiply it by s. And then we evaluate it at the limits of integration. And then we subtract and do the integration by parts, then 0 to t of, and then we take the derivative of this part, which becomes 1, and we have e to the k minus 1 s all over k minus 1. All right, and that's ds there. All right, so on this side, we have to now evaluate at the limits of integration, so that becomes x of t. That's what we want to solve for, right? Times e to the k t minus e to the k 0 times x of 0 at 0. Right, so obviously we can rewrite this now as x of t e to the k t. And this right here is just 1, so that becomes x0. X naught. That's our symbol for the initial condition value. And now we can continue on here evaluating. What we have here is I have to evaluate now at the limits of integration. T e to the k minus 1 times t all over k minus 1 minus, and now when we evaluate at 0, we see because there's an s there, it just goes to 0. Likewise, we have that minus sign, and now we're going to take the integral of this. Here we see that this does have an antiderivative, and so we can take its antiderivative and evaluate it at its limits. E to the k minus 1 s, but now we have to divide by k minus 1 squared. And again, we evaluated the limits. All right, so I'm going to rewrite this part right here, e to the k minus 1 t all over k minus 1. And then we also have a minus now, and we're going to evaluate these endpoints here, and that's going to be e to the k minus 1 t minus 1, and then we're going to make that whole thing quantity all over k minus 1, quantity squared. Okay, so that looks pretty good. Now we need to solve for x of t. That's our objective. So what we're going to do is move that over to the other side and then divide everything by e to the kt. So we're going to do that now. We have, but before we do that, note that if I go e to the negative kt, which is equal to 1 over e to the kt, if I multiply this by e to the k minus 1 t, that's simply going to equal e to the negative t, right? That's an important observation. So when I solve for x of t, it's going to be equal to x naught. Again, I moved x naught over, equal to e to the, times e to the k negative kt, and then we have a plus, and we're going to multiply. Again, we're going to multiply e to the k negative kt by this. We're going to get a t e to the negative t all over k minus 1. Looking good. And then finally, we have a plus. Now I see I have a minus there, but I'm going to change that to a plus. Just flip the signs of these around, or flip the order of these around. And then I'm going to have a e to the negative kt, because we're multiplying everything but e to the negative kt, minus e to the negative t all over k minus 1 quantity squared. So there's our solution. Now, of course, k in this case, And the particular solution that we had, or the particular parameter we had, was k equals -5. So we just have to know that k minus 1 is equal to -4/5. All right, and I trust that you can plug that in everywhere appropriately. The next thing we want to do is maybe assess what this looks like. I mean, I need to plot this. And recall, of course, that the original input, the original input, our q of t, that was our c in times r in of t. That was t, oops, I'm going to rewrite that there. That was equal to t e to the negative t. That was that little pulse, and I can draw out a picture of that. That was that pulse that goes like this. Right, the question is then, if here is x of t, I want to find what c out's going to look like. Remember that c out was equal to x all over v. So all I have to do is divide this by v. Let's divide everything by v, just a constant. Now I want to know what it looks like. It should be something like this more. So that's c in, and that's c out. And now to verify that, I just actually pulled up my MATLAB, so I can pull that up here. Oops, that's not it. There it is. Okay. Now I just wrote out this little script, this little function here that's going to plot it for me, and I've computed it right here. I have it sitting right there. So I want to know what it looks like for the particular parameters I chose. So I'm just going to hit play on this, and here's what my solution looks like. And I see here in the blue is my C in, that's that concentration in, and you see it goes up like that, and it peaks pretty quick. Because remember, this was like a pulse of salty water that I injected into this clean freshwater tank. But we see what happens later is that the concentration out, there's a delayed response. That pulse of salty water mixes with the large volume of fresh water, that 5 liters, and slowly the concentration rises, but there's a delay in the peak. The peak happens at a much later time, in hours. And then eventually, though, as the pulse of salty water decays down and it's going to 0, the concentration of salt in our tank will eventually also diminish. So we see that basically what happens is that if we have a pulse of salty water going through it, this tank, this large tank of fresh water, acts as sort of a buffer. It's going to delay and subdue that response because that salty water is essentially being diluted into a bigger tank of fresh water. Anyway, so that's the idea of how we can study these solutions. And what I'm going to do is also take this little script, and I'm going to I'll post this MATLAB piece of MATLAB code in with your other announcements in class, so you can play around with this and use it and experiment with different parameters. All right. Anyway, so here's our solution down here, and hopefully that clarifies the methods of solving using first-order linear equation methods, and also how to use these methods to model problems involving mixtures inside tanks. So thank you very much.